My name is Shoa Omobego. I will be the moderator for this public forum. First, I need to thank you for coming to this forum. I know it is very important for us, that is the shared program, for hosting this forum, and also for you to have taken your time to spend this moment with us. Please, the lunch is across the hall. You can grab something to eat if you've not done that. You can also take a bottle of water. First, I would like to introduce the panel, the panelists, who will be speaking from their own vantage point on the school shelter in Oklahoma. Specifically, we are looking at the issue of storm shelter in Oklahoma public schools. The effort to hold this discussion is based on what happened last year with more elementary school, in which 7 students lost their life. After that incident, we had intensive public debate as to what kind of policy we need to develop in Oklahoma in terms of protecting kids while in school. Other states like Alabama, Missouri, they had similar experience, and they developed their own public policies to address how to protect kids in school. More importantly, it is about funding. How do you fund the construction of school shelters? Or how do you retrofit schools with safety environment? And this has become a debate in Oklahoma here. Our panelists will talk on this. I need to inform you that OU has taken no political position on this issue. They make no claim as to which policy is best for Oklahoma. But it is just a public forum to discuss the issue of school shelter. My immediate left is Brian Walker. He is an expert in terms of school shelter. And let me read a very few points from his bio, which you have, and I don't need to read everything. He's an engineer, professional engineer, with Wallace Engineering, a structural and civil engineering consulting firm headquartered in Tulsa here. He holds master's degree in architectural engineering from Oklahoma State University. I won't go between the rivalry with OU. But we are glad to have you here. For the past 30 years, he has engaged in a variety of engineering projects, including designing healthcare centers, educational and sport facilities, high-rise office building, retail building, remodeling projects, industrial and warehouse facilities, including aircraft maintenance hangars, multifamily residential projects, and hotels. So he had a lot of experience to share with us in this forum. So my left again is my colleagues from NOM, Dr. Peter Wachter. He's an associate professor at the University of Oklahoma College of Architecture Division of Interior Design in NOM. He had 3 master's degrees, and every one of them interrelated in terms of architectural not just an architect, but he's also an artist. So we always call him Aki. So bear with me. We really welcome you. We appreciate you coming from Norman to spend this time with us. And also, he may want, no, he does not like to talk about it. He has just gotten a grant of $1 million in terms of school environment, safety in school environment, and he will talk about it during his presentation. Please join me in welcoming our panelists. Dr. Ballard will join us later on. I need to tell you that the other speaker, Mark Nestle, cannot be with us today because he was very ill this morning. He emailed me early this morning to tell me that he would not be able to make it. And then the other guy, John Bordeaux from FEMA, could not get out of Texas last night because he was informed very late yesterday morning that he needs to be coming to home. But I can assure you, with the expertise we have here this morning, you will not regret being here. Thank you so much. I will now hand over to Ram.
Is there a remote control?
I will do it for you.
Oh, all right. Well, as Shola explained, I'm a structural engineer, over 30 years of experience. I did have some experience with shelter design. I was involved with the design of the City of Tulsa 911 call center, done shelter design for various schools, and data center design, which usually has criteria very similar to shelter requirements. I have a slideshow that I've put together and presented a few times. I've tried to pare that down some for this event. If you go ahead and advance the slides, we'll kind of try to run through that quickly and see if I can enlighten you on anything.
Yes, ma'am.
Yeah, go ahead and advance the slide. I recently completed training with Oklahoma Emergency Management, FEMA, for the Safe Schools 101. It's a program that was set up after the May tornadoes of last year, somewhat as a stopgap measure. I think there's something like 1,800 schools in Oklahoma, and by some accounts, more than 60% of them don't have shelters. My guess is it's probably quite a bit more than that. And of course, as you've heard, and you've probably seen in the news, there's some funding issues, and that's kind of making progress a little bit slower than we might like. What this program does is there's training for design professionals like architects and engineers and school administrators to help them go through a process for identifying areas within their existing facilities that provide the best available area of refuge. And that's a very specific term of art that's used by FEMA. It doesn't provide really life safety, but it just, because of the construction of the school and the layout of the school, it works out to be the best area. So I just completed that training about a month ago, and this is just sort of an example of what the results look like. Obviously here, what was identified was the corridors, and that's usually going to be the case. It still, a lot of times, just boils down to common sense that we've heard over and over again. Find the smallest interior room and shut the door. Go ahead and advance the slide. Of course, this is what's being done now in most schools, and it would be classed as an area of refuge. It's just a corridor, and it's sort of a duck and cover technique. Unfortunately or unfortunately, that's for most schools, that's about the best they can do right now. Fortunately, the probability of an individual building being struck by tornado is pretty low. So go ahead and. In terms of design for shelters or in retrofitting an existing structure, the hazards that we have to consider in the structural design would be, of course, the wind pressure, though that's may not be as critical as the literally the impact of debris on the structure. And that, that can range from small debris, like pieces of lumber, through bathtubs, cars, and large, like propane tanks or trucks or things like that. Another issue is lay down and roll over, lay down of a tree or adjacent tower or something like that on the structure. It can be a hazard if there's something. In the school assessment that I did through the Safe Schools 101, there were some portable structures, portable classroom structures adjacent to the building, and they were not tied down particularly well. So we identified those as a rollover hazard, and that kind of impacted our perception of the best available areas of refuge in that school. Go ahead and advance the slide. This is just a quick map. You may not be able to see it very well, but it comes from FEMA, and it describes the wind speeds that we have to design for. And for most of Oklahoma, if we're designing a genuine tornado shelter, we're going to be designing for a 250 mile per hour wind. This was actually a little video, but I'm not sure it's going to play, but there's enough there that you kind of get the idea. This is, what the wind does to a building as it blows across the building. And you can, the blue indicates the, higher pressure. So you can see that on that windward wall, which is to the left and front there, there's a high pressure there, but then as you go up over the roof, the wind picks up speed and creates an increased suction on the roof, and so you've got high pressures there at the leading edge, and that's why a lot of times you see roofs peel back or lift off from one side to the other. And of course you get suction on the side walls and you get suction on the lever walls. Go ahead. Just kind of an example of the pressures that we deal with when we convert the wind speed to a design pressure. Normally for buildings, per the building code, we design for a 90 mile per hour, 3-second gust. We go through calculations that are prescribed by the building codes to come up with pressures to apply to the structure that we're modeling. You can see, in this case, the wind is coming from the left, so that wall on the left is a windward wall. There's a positive pressure from the outside there. You can see on the wall on the right, which would be the leeward wall, there's actually suction. Some people find it a little hard to accept that wind sucks, but it does. And then, of course, there's suction on the roof. We also have internal pressures. The building gets pressurized, and in some instances adds to that external pressure. You can see that it increases the pressure on the leeward wall and the pressure on the upward pressure on the roof. So just to look at a quick number, let's just look at the roof. We're at about 20 pounds a square foot that we're designing for. Go ahead and advance the slide. This is a 250 mile per hour wind going through basically the same equations and the pressures that we come up with. And you can see that on that roof we now have about 156 pounds per square foot. So we went from 20 to almost 160 pounds per square foot. So it does have an impact on the demands on the structure, and that in part drives cost. It gets even worse if an opening is breached. If there's a window or a door that's breached by debris or it doesn't withstand the wind pressures, then the building starts to kind of inflate like a balloon, and the pressures go up even more dramatically. You can see that the upward pressure on that roof just went up to 245 pounds a square foot. Just for reference, an office floor, when we design an office floor just for live load that's going to be on that floor, we design for 50 pounds per square foot. This is 5 times that acting up. Go ahead. The other thing, and probably the thing that's often more critical, is the windward debris. Go ahead and advance. There's some examples of some smaller debris. You can see the two-dimensional lumber that's penetrated the refrigerator. You can see some laying on the roof. You can see where it has penetrated that roof, and you kind of see on the face of that wall that it's really been pelted by a lot of debris. And it's hard to tell whether that window is intact, but I'm doubting that it is. There's some examples of what would be called medium debris, a bathtub and a boat. And to give you an example of how far that stuff can travel, I think in the most recent tornadoes, there was a news report where they found a door, and they identified where it came from, and it was 20 miles away from its original location. So this stuff can be carried quite a distance, and it reaches some pretty phenomenal speeds. This would be considered large debris. You can see the I-beam there, the steel I-beam on the left. I guess it must be a very aerodynamic shape, because it's certainly very heavy. But it was obviously picked up and hurled. There's a large, looks like maybe a propane tank there. Those get picked up, and I think we've all probably seen the news reports and videos of all the semi-trailers that got tossed around last year. Lay down and roll over. There's probably one that everybody's seen before. But on the left, you see essentially, I think it's a double wide home, manufactured home that's just rolled over. On the right, that's a semi-trailer that's rolled over into the structure. So, when those hazards exist as known hazards adjacent to a structure, we want to take those into account in the design. Lay down on the lower left, that looks like it was a construction crane that was taken down in the van. On the upper right, that's just a large mature tree that toppled onto the house. So those are examples of lay down. So we do have some guidance on what to do. I don't recommend that you take anything you saw in the movie Twister very seriously. I do not recommend tying yourself to a rappel. But, and I don't think FEMA or anybody else will either. We talk about two types of shelters when we start talking about designing shelters. There's the residential shelter, and then there's a community shelter, and the distinction is made by number of occupants. Once you have more than 16 occupants, it becomes a community shelter, and the requirements are a bit different. You have to start providing a little bit more than you would for a residential shelter. The residential shelters are governed by ICC, that's International Code Council 500, that's a standard document that's adopted by the International Building Code, 2009 International Building Code. And I think I was telling someone earlier, the International Building Code 2009 does not require you to build a storm shelter anywhere. But if you elect to build a storm shelter, it has to meet the requirements of ICC 500. I understand that the 2015 edition of the IBC will require storm shelters in school buildings and other facilities with similar occupancies. FEMA 320 has been a long time kind of prescriptive guide for design of residential shelters. When we get into community shelters, we're looking at ICC 500, which just came out in 2008, and then FEMA P361, which has been around for quite a few years in various different formats. There's an example of residential safe rooms. I think everybody's probably seen those before. You can, after this, you can probably take a trip over to Promenade Mall, and I've seen them over there on display. And then you also see an example of some large debris there resting on top of that one on the left. Okay, probably a good time to make a distinction here between what's called a shelter and what's called a safe room. And you'll hear those used a lot, and you'll hear them used interchangeably. And you really, as design professionals and people that are discussing this, I think with the public, you have to be careful about your terminology, and I think you want to define it because they're both terms of art. If you design per the requirements of ICC 500, you have a shelter. If you design per the requirements of FEMA P361, you have a safe room. And for tornado resistance, there's not a huge difference. It's really more of a difference when you're talking about hurricanes. But in terms of applying for grant money, in terms of the expectation for performance, there is a difference. FEMA defines a safe room as basically a shelter with it provides near absolute protection. The only reason they won't say that it provides absolute protection is we don't really know what the extreme event is. We're designing for a 250 mile per hour wind, we're designing for specific debris loads. But we don't know that that's the most extreme, so FEMA isn't going to call that absolute safe. It's near absolute. According to them, a shelter doesn't provide that. My personal opinion is that if it's done right, it does. But when you're talking to your client or the public, you want to make that distinction. You don't want to build false expectations about what they're getting. We also have clients frequently that tell us at the beginning of a project they want a storm shelter. When we start to discuss what that's going to entail and they start seeing the costs, they kind of back off from that. And well, geez, can't we just make some walls a little bit stronger here and there? And certainly you can do that sort of thing, but you really have to be careful that you don't describe that as a shelter. It's still, at that point, that's still just a best available area of refuge. Next slide. Okay, this is just a slide that kind of illustrates the different levels of protection. Good protection is described as the best available refuge area, and that's what we're currently doing with the Safe Schools 101 program, where we go in and make assessments and identify that best available refuge area. A little bit better than that is the hardened area, which I described, where maybe we make the walls a little bit stronger, maybe we give it some debris impact resistance, but it's not designed to all the requirements for shelter or safer. And of course, then the best is a safe room or storm shelter. This is another table that kind of explains a little bit. That first column is just, it may be what the school is doing right now. They're ducking cover in hallways, or God forbid they're in the gymnasium or wherever they're going. It's just what they're doing now, but they haven't had any guidance from a design professional on whether that's the best thing to do. The next column over is once they get that guidance, that's the Safe Schools 101 assessment, and you actually identify those best areas. And then you step over to a hardened facility, which again is just strengthen the wall, increase resistance to debris impact. And then we move into the storm shelter and the safe room. And those are designed by a professional in accordance with the requirements of ICC 500 or FEMA P361. I will tell you, FEMA P361 is a guide, it's not a code, it's just a guide. But if you're going for the FEMA grants, you've got to comply with it. Okay, these are the current codes and standards that we're using. IBC 2009 is adopted by the city of Tulsa. I believe the state of Oklahoma has adopted it now too.
Yes.
Okay. And then that, as I mentioned earlier, references the ICC 500 for shelter design, which provides some minimum requirements. And then there's FEMA P361, which again, if you want to achieve that safe room status and apply for the grants, that's what you're going to have to comply with. And if you comply with that, you will be complying with ICC 500. ASC 7205, that's just a standard that engineers use for calculating loads on buildings, including wind loads. Some of the structural design criteria that we're faced with, we have to design the roof of the shelter for 100 pounds per square foot live load. And as I mentioned before, for an office, we're designing for 50. So we're upping that downward gravity load that we're designing for. That's to account for debris that might accumulate on the roof and that sort of thing. We're designing for wind pressure based on that 250 mile per hour wind. ICC 500 has some provisions that allow you to mitigate some of that pressure through atmospheric pressure change through venting. One thing to be careful about with venting is that any penetrations in the shelter have to be protected from debris. So my preference is to not try to do that so that we don't have to protect a bunch of penetrations that we otherwise would need. And then of course there's the debris impact, and there's impact on vertical surfaces, which would be a wall. And the model debris that we designed for is a 15-pound 2x4 traveling at 100 miles per hour. And we use we don't actually go through any calculations for that. That's all done by test. Texas Tech in Lubbock kind of started this many years ago. They're well known for their wind research. And they developed this debris impact criteria, the testing for it, and now quite a few others, universities and private testing labs employ it. But they literally shoot the 2x4, 15-pound 2x4 at an assembly. If you have a door or a window or something you want to have tested, you send it to them, or if it's a wall assembly, you send it to them, they set it up in their testing apparatus, they shoot this 2x4 at it, and if it penetrates, you fail. And if you're doing a door, they shoot it at different points on the door, and the door has to remain intact and latched. For vertical surfaces, we look at a 15-pound 2x4 traveling 67 miles per hour, and I think that's probably considered the terminal velocity of something just free falling. Next slide. Some additional structural criteria I mentioned before: the lay-down hazard, the rollover hazard. If you're situated next to a much taller building, there's a collapse hazard that building might collapse onto your shelter. So, you know, we want to look at the environment that we're in as well and try to account for those things when we can. Some other requirements: the floor of your shelter, the community shelter, has to be located 2 feet above the 100-year floodplain. And then for the architects, there's some calculations for the number of occupants based on area, of course. You're familiar with those kinds of calculations. But for the shelter, you allow 5 square feet usable area per occupant. So if you're looking at a gross area of a room that's empty and going to remain empty, then you get to use the gross area. But if you've got furnishings, particularly fixed furnishings like this, you have to reduce that area. So you take, if we were using this room, which might be a good candidate for a shelter space, we would take the gross area and then cut it in half because of this fixed furniture. And that would be, then divide that by 5, and that would be the number of people that we could propose to shelter in this space. And then you have to allow for wheelchair access and 1 wheelchair space for every 200 occupants. Another issue that comes up is means of egress. You have to have 2 ways out of the community shelter. One of them can be a hatch. If you're in a space like this, if we use this space as a shelter, it would be what we call a multi-use shelter, because it's used for normal everyday operations as well as a shelter. So your egress requirements would probably be based on its normal use rather than the shelter use. You have to have separation from if you're building the shelter within an existing building, you have to have 2 layers of separation, fire separation. FEMA wants you to have NICC wants you to have a fire extinguisher in the space. You've got to think about ventilation. You can do that with natural ventilation or with mechanical ventilation. Probably with a multi-use space, you're going to use the mechanical ventilation. But again, those penetrations have to be protected from the debris. And if you are using mechanical ventilation, it has to have an uninterrupted power source, a generator or something, and that generator will need to be protected as well. I've mentioned penetration protection several times. Any doors that go into the space have to meet that missile impact test. You can do a shelter without a door, but then you'd probably do a baffle system to deflect any debris from just having a straight shot into this shelter space. There aren't many windows that you can put in a shelter space because they just don't muster the debris impact. I remember when I started the design of the 911 call center for the city of Tulsa, the architect called and asked, "So how big can our windows be?" I said, "What windows?" And I think they may have found a very small window that I have to test it. There may be others now. I think at the Safe Schools 101 program, I saw a couple small storefronts that they claim have met the debris impact test. So, but you really have to find those, and you have to have your paperwork that shows that they've been tested properly and they've passed. Sanitation facilities. Once you get over 50 occupants, you have to have some sanitation facilities. It's 2 minimum with 1 per 500 occupants for toilets. those don't have to be, flush toilets with plumbing and all that. They can be chemical toilets. I even think in terms of like camp stools or something like that. Hand washing, I think, again, it doesn't have to be plumbing. It can be, I would think it can be hand sanitizer or something like that. But remember, in a tornado event, in a hurricane event, I think you have no choice but to put plumbing in there. But a tornado event, they're going to be in there 30 minutes to an hour or something like that, maybe. You should have a first aid kit in the space, emergency lighting for at least 2 hours. When you're designing these, you've got, of course, as always, you have to think about accessibility, and then there's very specific signage you have to have that identifies the shelter. Cost, what a lot of people are interested in. If you're doing a single-use safe room, say a standalone building that you're only going to use for sheltering people during an event, that's going to run you around, on average, about $230 a foot. If you're building a new facility and you're going to incorporate that shelter into a space that's used within that facility for other purposes, so you're basically doing part of the structure is hardened and protected, you're probably going to see that go up to about $265 a foot, just for the wind pressure protection. And when you throw in the debris impact resistance, it's probably going to go up to around $310 a foot. What you want to remember with that is it's not the whole building that's costing $300 a square foot. It's just the area that you're defining as your shelter. And then to retrofit a structure, an existing structure, I guess the sky's the limit there. It depends on how robust that structure is to begin with, but it can run you, easily $350 a square foot. If you're going for the FEMA grants and you're trying to get financial assistance, you have to go through their cost-benefit analysis and show that there's benefit to the shelter. I personally understand how they come up with the cost. I'm not sure how they measure the benefit of saving lives. Anyway, I haven't actually been through that process. I just know it's out there. And there's a website there for grant applications. And then they do have some guidance and handbooks for those applications as well. Just some quick, we'll kind of breeze through these. These are some examples of some shelter schools that we've designed. This is for Edmond Public Schools. They selected, I think, 4 classrooms to be used as shelter space. And in this case, we did it with concrete masonry. That masonry is grounded solid, every cell, and it's reinforced. I didn't personally do the design on this, but I would guess it was probably certainly no more than 32 inches on center, probably 16 inches on center. So a lot more than we typically see in a masonry building. Okay. That's sort of the inside of the space. You can see, for those of you that are in the profession and in the industry, those roof joists look a lot heavier than you're probably accustomed to seeing. They're spaced much closer together, so you can see that's where some of your cost is. There's going to be concrete on that roof deck as well, because metal deck will not provide the resistance to the missiles. And then also you need some dead weight to resist that uplift. This particular classroom did have some windows. They kept them small, about the size of a pedestrian door, and then they bought tornado-rated, debris impact resistant doors to use like shutters. So when they have bad weather approaching, they've got a watch or whatever, the teacher goes and closes and latches that tornado door over the window from the inside, and the window will break, but the debris and the shards of glass won't come into the space. This is another case where we have storm shelter built within a structure. I think this one, go ahead for a second. It's basically built concrete walls, and we're tying joists into it. Excellent. There's sort of an example of what the foundations look like. Have a little bit more reinforcing than you might normally see. The footings are maybe a little bit bigger to resist those upward forces and overturning forces. So expect larger foundations, more reinforcing steel. Excellent. Just some more pictures of the concrete walls. There's how we frame the roof, steel beams, spaced pretty close together. Those are like they're about maybe 3 or 4 feet on center. Heavy form deck on top. There'll be concrete placed on top of that. You can see in the foreground there the heavy steel angle. That, I told myself I wouldn't get too technical here, but I can't resist. When those beams are subjected to uplift, the bottom of the beam goes into compression, and it's not as stable unless you brace it. And that's so we wind up with, and we call that bridging, and that gets heavier in the shelter design. Okay, I zipped through that as fast as I could. I apologize for taking more time than I was allowed. But if there are any questions, I'd be happy to field those.
We will continue the question during the open discussions.
Okay.